Okay, we're going to talk about Euler's method, or Euler's method for a couple differential equations. Now, in an earlier section, H12F, we talked about how to do coupled differential equations. We discussed what phase portraits were, and we talked about how to find eigenvalues and eigenvectors to come up with our particular solutions, and using our particular solutions to draw our phase portrait. Okay, so, but if we've got an equation that there are certain times when we have to use Euler's method. So, and when we're dealing with if we've got some data and we want to know how it works over time, like I said, there's times when we've got to use Euler's method. Um, so, anyways, it's very important that you watch the IB vodcasting video with Pablo Sanchez. It's so good. He explains it super, super well. But if you, we're going to be using the calculator a bunch, and if you go back to handout H11N3, and I've got the calculator instructions here. So that should be like a beginning refresher. The only thing additional is we've got instead of in dx dy or we also have a third variable, time. Okay, and these are the equations that we're going to be using, and make sure you're in sequence mode, and second 9, it gives you our omega symbol on your calculator. Okay, so if you want to copy my notes, because Mr. Pablo Sanchez, his handwriting is quite messy, so you're welcome to hit pause and copy my work. And like I said, you can hit pause, but you need to hear his explanation of how he does it. These are screenshots of his results on his calculator. So you really need to go do screenshots on how to do this. So let's do the next one together, which is a problem that I found in the textbook from the Oxford book. Okay, so use Euler's method with a step size of 1.0 to find the approximate values of x and y when t equals 1 and when t equals 2. Okay, so here's my differential equations, and we're going to start off with when x is 4, y is -2, and that's when time is 0. So those initial values of 4, -2, and 0 are going to go in these spots on the calculator. So, where's my pen? So 4, -2, and 0. Okay, so this is my x, this is my y, this is my t. Okay, and then my first equation for my x is this. So this is the same thing as x dot means dy dt, and y dot is okay, that's x dot is dx dt, y dot is dy dt. Okay, anyways, so I'm going to rewrite this using the Euler's calculator method, and so using this relationship, which is seen in your IB formula packet. So I'm going to retranslate the 3 lines that we need here. So I'm going to write this as x subscript n equals xn minus 1 plus my step value is 0.1 times, and now I'm going to fill in my function here, which is 3 and x, so we're going to, okay, I'll just put the x subscript n minus 1, and then minus 4, and then y subscript n minus 1, close parentheses. So the open parentheses is, all of this is getting multiplied by 0.1. Okay, y subscript n equals y subscript n minus 1 plus 0.1 times, and then this part right here goes into the calculator. It becomes xn minus 1 minus 2 times y n minus 1, and then we've got the t. This one's not going to really change ever. T subscript n minus 1 plus 0.1. And this is going to help us calculate our steps, our estimation of the approximate values of x and y using Euler's method. Okay, so so how do I type this into the calculator? So I rewrote it like this just to help me see what it is that I am going to input in the calculator. And now we need to remember that for x, y, and t, we're going to be using u, v, and omega. Okay, so the first line here, I'm going to be writing u parentheses n minus 1 plus 0.1 parentheses 3, and this is x, so I'm going to write u parentheses n minus 1 minus 4 v parentheses n minus 1, close parentheses, okay, and the next one is going to be v parentheses n minus 1 plus 0.1 open parentheses u n minus 1 minus 2 v n minus 1, close parentheses, and then the last one is omega parentheses n minus 1, close parentheses, plus 0.1. So this value here is my step value, and this right here is my differential equation, and the other part is always going to be there when you're using Euler's method. And like I said, this is in your formula packet. You don't need to remember. So the H here is my step, and Pablo Sanchez walks you through that. So all right, so let's type this into my calculator. For the other examples, I'm just going to show you what I've I'm just going to show you my key. Okay, so so I've already entered in. Okay, so let's. First thing, I like to add the pink numbers first. So let's put in 4 there. The y minimum is -2. And then this one is 0. Okay, it's already at 0. Okay, so I've got the pink numbers in already. 4, negative 2, 0. Okay, let's go to the first line here. U subscript n. So I've already done a lot of different problems here. So I'm just going to, from this point right here, I'm just going to hit delete. Okay, and then from this point right here, I'm going to hit delete. Okay, and so now let's type in our green information. Okay, 3, and then U, I hit second 7 to get my U, parentheses n minus 1, close parentheses, minus 4, second 8 to get my V, parentheses n minus 1, close parentheses, close parentheses. Okay, now let's do this other line. Okay, U, parentheses, n minus 1, close parentheses, minus 2, parentheses, V, parentheses, n minus 1, close parentheses, close parentheses. Okay, and I should have everything here all written. So I do second graph. Sometimes it takes a little bit of time. Go drink some coffee. Okay, oh, it started at a high end. So if you wanted to start it out at 1 or 0 or something like that, we can change the table set, this blue one. So I hit second window to change my table set. Let's start at 1. Okay, now let's hit second graph again. Okay, so we're trying to figure this out when, so from the table, so we have our value of n, x, y, and t, right? So when we're at 0, our x value is 4, our y value is negative 2, and our t value is 0. Okay, so and now we're wanting to go when our t value is 1. So when our t value is 1, so these were the original ones we plugged in, and we're looking at the table. So now I'm going to go hit the arrow a couple times. Okay, so now I want the t value to be 1, so I'm going to arrow down until I get to 1. Okay, so when t is 1, my y value is 10.98, so let's call that 11.0. Okay, and my x value is 48.1, and my n value is 10. The n value should make sense because we had a step size of 0.1, and we're going up to a t value of 1. Okay, so they asked us to find the x and y values when t is 1, and also when t is 2. Right? We want to find it when t is 2. So we want to find the x and the y values when t is 1 and when t is 2. So here is my x values, my x and y values when t is 1. Now we're going to figure out the x and y value when t is 2. So I'm going to arrow down. It takes a little bit of time sometimes. My n is going to be 20. Okay. So at 20, my x value is 306. and my y value is 76.2. Okay, and so what did we do? We hit the arrow down. We hit the arrow down until t equals 1, and then we did the arrow down until t equals 2. Okay, so you pretty much just do that for all of these handouts, for all of these problems on this equation. I can't even speak. So, okay, this is the same thing you just did with a little screenshot. Okay, on the next page. Okay, same process on the next one for part B. Oh, okay, so for part B, this was the same differential equation that you did on an earlier handout, but these were exact from when you did your 12F assignment. So when you use your when you did 12F and you plugged t into your coupled differential equation, you got these values. Okay, and they wanted you to figure out percent error. So percent error is the approximate value minus the exact value divided by the exact value, and then multiply that by 100 to get your percent error. Okay, I'll just hit pause for you to look at this and think about it. Okay, so the next problems were in your textbook in 12H. So all I did was rewrite the 2x plus 2y. I rewrote that there. 5x minus 5y. I rewrote that there. And then I converted it to my u's and the v's. This just kind of helps me figure out how to write it into my calculator. And then I arrowed down till t equals 1. Okay. For part B, they wanted you to compare your answer to what you did on the 12F number 1 handout, and the particular solution from the 12F number 1 handout was this. So we're trying to figure out when t equals 1, then to get my exact answer, I plug in 1 in for here, and then I got these exact values for x and y. Now, as you recall, when you did 12F, that assignment was very labor intensive to figure out the x and the y value at a particular t time. So Euler's method is definitely a lot faster, because as you remember, the 12F assignment, it took me 2 pages of calculating in order to get my answers. So, but if you look at these answers, clearly like 57 and 58 compared to 109 and 110, Euler's formula severely underestimates the value of x and y. So, which one's better? I think if you want a really exact answer, then you're going to be doing what we did on 12F. If you're just wanting super approximate, but this is not really that close, then sometimes the Euler's method is close, as you'll see in a later example. Okay, so here's problem number 2. Once again, I just rewrote the the x plus 2y, rewrote that here. 3y, I rewrote that there. Hit pause if you need to. And if I compared my answer to what we did in 12F.1, I just plug in 1 in place of t, and then I get these x values. So this is my Euler estimate. This is my estimate this is the exact solution exact answer from the particular solution from 12F, and you could see they're in the ballpark, I guess. Still, the Euler's method underestimates the x and y values. Okay, the next problem's just wanted you to practice Euler's formula. So hit pause if you need to. And then after typing into the calculator, you got these answers. Okay. These were examples where the equations get a little bit crazier, because the differential equations have x squared and y squared, and these you would not necessarily be able to do easily with the methods that we did in 12F. So in examples like this, Euler's method is significantly easier to implement. It seems like all of these problems had a step size of 0.1. I don't know why they were in love with that step size, but that's what it seems. So, okay. Oh, here's the answer. Okay, pause if you need to. Okay, is this the last question? Last question. Okay. Same stuff. Once again, with the x squareds and the y squareds, and oh, look, this even had t inside the differential equation. This was something that you would not be able to do without using Euler's method here. Okay, so here are the what you would type into your calculator, and these are your answers of x and y when t equals 0.5.